All right, so let's talk about intermolecular forces. If you haven't seen the video on functional groups, check that out first. Intermolecular forces are basically affected by the functional groups that are present within a molecule. And the definition of intermolecular forces is basically the forces between molecules, right? So, forces between molecules. And so this is definitely a review from general chemistry, but we'll go over this still. It's really important because it does affect the physical properties as well as so let's see. The first one is going to be London dispersion forces. Dispersion forces. Oops. And these are also known as van der Waals. Forces, right? And so these, or actually another name, aka instantaneous dipole. Okay, so the instantaneous dipole is actually more telling as to what it actually is. I'm going to abbreviate that. And so every single thing has London dispersion forces, and that's because it's anything with electrons, right? And so this is going to be the weakest of the three forces that we're going to be talking about. And also I'll write it down. Everything has this, or these forces. Okay. So the best way, or the strongest, I guess the molecules that only have London dispersion forces, some of them have stronger London dispersion forces than others. And so the largest surface area is going to have stronger intermolecular forces. Largest surface area. Whoa, my words just disappearing like that? That's crazy. Surface area equals stronger intermolecular forces. So IMF, intermolecular forces. Okay. And that would be like a molecule like long and skinny versus just circular like that. Okay. And one of the cool things about London dispersion forces is that's pretty much how geckos work. So geckos use this, and it's because they have in their little paws, whatever you call them, their cute little feet, they have a bunch of like, almost like, you can think of them like hairs. You guys probably, most of the bio majors will probably know this better than I would anyway, but I think they're called like cilia or something. I don't know. It's just like, imagine a paw, cute little paw, whatever. There's definitely not. Let's go with like, how do you draw a gecko paw? Let's go with that, whatever. And then they got like little hairs on them, like a gazillion of them. And the reason why these are important is because it creates a lot of surface area, right? And so this is going to allow for a greater number of intermolecular forces, specifically London dispersion forces, and that's what allows them to stick to everything. But did you know they can't stick to Teflon? Wait, what? Geckos can't walk on Teflon? No, they cannot. So Teflon is PTFE. So you know how like you'll have certain polymers and they'll be like polyethylene or whatever. PTFE is polytetrafluoroethylene, and it's basically a bunch of these guys. So this is tetrafluoroethylene, and you make a polymer out of this. And since it has fluorines on there, fluorines are actually really small and they're really electronegative, and so especially relative to like the other halogens, they're small, and so they are something that we would call not very polarizable. So the concept of polarizability is basically in that in an atom that you can easily induce a dipole. Okay. So polarizability, or an atom that is polarizable, is easily induced dipole. And so the bigger the atom, so let's say we've got fluorine, chlorine, bromine, and iodine. Iodine being larger is more polarizable. Okay, more polarizable, and so therefore it has, since we can easily induce a dipole, that means that we can kind of manipulate the electron like sphere, if you will, around the iodine, and rather than maybe looking like this where it's like a decent size or a decently shaped circle, we can manipulate the dipole and have it kind of favor one side in terms of like this is really delta negative and this is not so much. So this side right here, maybe you can consider it more delta positive on this side. Just think about the electrons kind of going around in circles around this guy, or moving everywhere, but then very briefly they all end up on one side, and that would be like this side over here. And since all the electrons are on one side, you get a delta negative. And if all the electrons are on one side, then that delta negative is there. That means the opposite side must be delta positive. And essentially, a delta positive will match up with a delta negative of another iodine, for example. And so that's how you get those intermolecular forces. The positives match up with the negatives, and the negatives match up with the positives. Okay, so basically you get stronger London dispersion forces for larger atoms. Okay, so larger atoms equals more polarizable equals more intermolecular forces. Yay. But poor little fluorine over here is very, very small and not very polarizable, and so we don't get very good London dispersion forces going on that, or an instantaneous dipole on the fluorine, and so poor little geckos can't walk on it. I tried to get a video from my my brother-in-law. He's got a crested gecko, I think it is, and he's I guess he doesn't like to come out much. So unfortunately I didn't get you that live video, but maybe I can get that soon, and I'll just throw that at you later when it's less relevant. So let's see, we've got our London dispersion forces, and that should be it for those guys. The compounds that are most commonly associated with having London dispersion forces are those that don't have a heteroatom, and so those would be like your alkanes, so something like hexane. Alright, so let's move on to the next intermolecular force that we want to discuss, and that's going to be dipole interactions. Okay, and so dipole interactions are definitely just going to be somewhere in the middle in terms of intermolecular force strength. Okay, so middle strength, and that's because they're going to have an actual like solid net dipole, so they have CZ bonds, and then that's going to cause a net dipole. So for example, this particular carbonyl group right here, we've got a net dipole, and that's going to create a delta negative here, and then a delta positive on that carbonyl carbon, right? And so that means that we have that net dipole, and so if we've got a combination of positive and negative charges, then the other molecules can interact with those, creating a stronger intermolecular force. Okay? And that's pretty much all we're going to add to dipoles. And then we're just going to move on to the last one, which is, hydrogen bonding. Hydrogen bonding. Okay, and hydrogen bonding, we definitely know this one already. This is going to be the strongest intermolecular forces. Okay, and these are basically when we have a hydrogen that's bound to an oxygen, a nitrogen, or fluorine, and it's attracted to an oxygen, a nitrogen, or a fluorine in terms of their lone pairs, or the delta negative that would be on there, right? And so super common one, right, is water. We've got water here. This is a delta negative, and here's all delta positive, and we should know that another oxygen from another water molecule which has a delta negative, can interact with the delta positive on the other hydrogen, and then that just happens over and over again with all of the molecules of water that are kind of mixed together in whatever container you have. And so hydrogen bonding is very strong. It's actually essential to life. It holds our DNA together, and it also is pretty cool when you pour a glass of water out and it doesn't overflow, even though it's occupying more than the volume of the cup, and you got that little bubble on top of it. So that's pretty much it for introducing our intermolecular forces, but we do want to bring up or discuss the physical properties that they do affect. Okay, but before we do that, we got to get some practice. Okay. All right, so let's talk about physical properties now. And so basically, physical properties are definitely going to be affected by the intermolecular forces. So if you have strong intermolecular forces, then it's going to increase your boiling point, for example, and as well as your melting point, and then your solubility is also affected by the intermolecular forces. Solubility. Okay, so let's go over the details of this rather than just take it for what I was saying. So let's do boiling point first. So the boiling point, basically the functional group determines the boiling point. Okay, functional group determines boiling point. So remember we were talking about pretty much alkanes not alkanes, but hydrocarbons as one of the functional groups. So hydrocarbons, these were basically non-polar substances, but then we also had those with the CZ bond, the sigma bonds, right? And then we had C double bond O compounds as well. So these were the three main functional groups, and these ones are non-polar. These ones are definitely polar. More polar means that we have potentially one, at least two, or maybe even three of the intermolecular forces that we discussed, being London dispersion forces, the dipole-dipole, as well as the hydrogen bonding. So if the more intermolecular forces you have, the higher the boiling point. Okay, so more intermolecular forces equals higher boiling point. Okay, and in addition to that, we also have something that's not necessary, maybe not intuitive, perhaps maybe it is, but if we have a larger surface area, so surface area, then we technically would have more room for electrons to kind of be shuffled around. You can relate this to the polarizability of something. So if we have a larger surface area, then we have a higher boiling point. Okay, and I do want to make sure that we differentiate between like a polarizable atom and then like a large surface area molecule. So I said you can think of it as polarizability because they are generally two different things. So something that is more polarizable also is something we want to make note of. More polarizable. And then that's, I'll put equals higher boiling point. And again, that's because you can have more intermolecular forces. So if you have something like, well, let me give you a couple of them actually. So if we've got this here, this versus this, there you go. Or let's say we've got maybe this versus this, right? Those are very similar as well. And then we can have 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5, 6. Okay, so all of these are very similar with some subtle differences, right? And so what's the subtle difference in this set right here? Well, it's not so subtle, I guess. It's this guy right here versus this guy right here. So where does that apply? That applies to polarizability. And so since iodine is more polarizable, this one would have the higher boiling point. Okay, so what about these guys? What's the difference between these? Well, it's pretty much the same atom count, but we have a different arrangement of atoms. And this is essential basically to change the functional group at the end. We have an aldehyde here and we have a carboxylic acid here. Okay, and so the difference between the two, although they are both very polar, the carboxylic acid has this OH group that can H bond, hydrogen bond, right? And so therefore this guy right here has the higher boiling point because it has all of the it has the London dispersion forces, it's got the dipole, and then it's also got the hydrogen bond. And whereas this one would only have the London dispersion forces as well as the dipole interactions. Okay, because they're all, other than that, they are generally the same surface area. And yeah, so let's take a look at this last one. This guy versus this guy, what's the difference? Well, they are isomers of one another because they have the same molecular formula, having 6 carbons and 14 hydrogens. But they are structurally different, obviously, right? And so this one right here is going to have a larger surface area SA, than this one, right? This one is more symmetrical. Okay, so this one is going to have the higher boiling point. You can think of it like here's a sphere of electrons and then here's a sphere of electrons, and so they can all, that larger surface area is allowing it to interact much better. Okay, so let's move on to the melting point. So the other physical property we want to discuss is melting point. And although very similar to boiling point, there are some subtle differences that we don't really want to confuse. And so we do want to understand what's actually happening when we're talking about boiling point and melting point. And so let's think about, like, so boiling point, for example, we have liquid going to a gas, and those molecules are no longer interacting with one another for the most part. When they become a gas, they're much farther apart and they're not strongly attracted to one another, whereas melting point, they are still going to be in contact, but when they're frozen, for example, or a solid, they are in a tight space. They're held much tighter together, and so they're closer in that sense, and so we want to keep that in mind as we go over these. So, for example, the first one thing I want to point out is they are similar. Boiling point and melting point, kind of the ability to increase each of those is similar in that if we have a stronger intermolecular forces, we will have a higher melting point, just like we have a higher boiling point. Stronger intermolecular forces equals higher melting point, right? If we have a more symmetrical molecule, we will have a higher melting point. And that's where this is a little bit different than boiling point. So more symmetry equals higher melting point. And we'll do a couple examples after this. So but basically what it's saying is, like, this one right here will have a higher melting point because it's very symmetrical, rather than something more crazy and branched. So let's see. We've also got well, I'm sorry, I need to add to that. So more symmetry equals higher melting point, and that's when we are comparing the same functional group. When comparing the same FG functional group. Okay, so let's take a look at some examples. When we're talking about, well, let's see, 1, 2, 3, 4, 5. Whoa, see, there goes my iPad just yelling at me, trying to make weird shapes and stuff. Minus 130 degrees Celsius, maybe versus this one. 1, 2, 3, 4, 1, boom. This is minus 96 degrees Celsius versus this one, which is minus 90. So think about this one. When we're talking about stronger intermolecular forces, which of these has a stronger intermolecular force? Well, obviously the OH, because it can hydrogen bond, and then this one because it has a dipole, and then this one is the last because all it has is London dispersion forces. And so that's why it has the lowest melting point, right? And then we can also compare. Let's just draw a line down the center and boom, boom, boom. That versus, I'll do it like this. 1, 2, 3, 4, 5, 6, 7. Oh, 1, 2, 3, 4, 5, 6, 7. Boom. And so since they both have, let's 1, 2, 3. Let's say we have, let's just throw something else. Oh yeah, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I'm sorry, I'm tripping. These both have 8 carbons and 18 hydrogens, and so they're pretty much the same, but this one has much more symmetry, right? This one's kind of wonky looking, I guess, and so since this one has more symmetry, it has the higher melting point. And that's what I meant when I was comparing this one, for example. And another thing about symmetry would be like benzene, for example. Benzene is actually, since all of these carbons in here are sp2 hybridized, it's actually planar. And so benzene stacks up really nicely with other benzenes. So you can have boom, boom, kind of just like perfectly stacked like Legos, if you will. And then they're just perfectly stacked. And so that's why symmetry allows for a higher melting point, because if there's better symmetry, then it's almost like stacking Legos. They're perfectly aligned with one another, and they can have stronger intermolecular forces in the solid state, and therefore they're going to have stronger intermolecular forces. They're going to have a higher melting point. Okay. All right, so let's go to the last intermolecular, or I'm sorry, the last physical property that we want to discuss, and that is solubility. Solubility. All right, so basically, what is solubility? It's the extent that a solute dissolves in a solvent. A solute dissolves in a solvent. Okay. Now, one of the super common things that you probably know already is like dissolves like. So what that means is polar dissolves with polar, and non-polar dissolves with non-polar. Okay. And then if you're somewhere in between, you dissolve with somewhere in between. Okay. And some things can kind of interact with a little bit of both, but generally just remember like dissolves like. So water and oil don't interact with one another, or they're not miscible, but water does. So water is here. Water does dissolve with ethanol because it's got that polar group. They look very similar. And let's just say hexane, for example, will dissolve in octane, and octane is like a gasoline, right? And so, or if we wanted, we can have some sort of oil, which was like, let me redraw that. One, two, three, four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, let's just draw 18. Because these would all, even though there is this particular functional group that is polar, there's a crap ton of non-polar portion of it, right? So that leads me to the last part of solubility, one of the criteria. So that means basically organics dissolve in water if it contains a polar functional group that can hydrogen bond and less than or equal to 5 carbons. Okay, so organics dissolve in water if it contains one polar functional group that can H bond, hydrogen bond, and has less than or equal to 5 carbons. Okay, so basically this fatty acid, it has a lot of carbon hydrogen bonds, like CH bonds, and is very non-polar on this portion. It is, however, polar on the left side of the molecule. Carbons. It is polar on the left side of the molecule, but if we look at this last criteria right here, it needs to be less than or equal to 5 carbons for each polar functional group. So we got this functional group right here, but we've got way more than 5 carbons for that functional group. And so therefore, this fatty acid is only soluble in oils or fats, right? And so that's pretty much it for the physical properties. And actually, so some terms that I want to cover for that particular or this section are going to be perfect for this particular molecule. Let's just say we've got this polar functional group over here, and then so this part right here, since it's polar, it's actually called hydrophilic, meaning it loves water, right? And the rest of it over here is non-polar. Whoa, 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 come on now, simmer down. So it's non-polar, and it is called, see, there you go with the shapes, iPad. It's called hydrophobic. So when you have a phobia of something, you are afraid of it, right? So this thing is afraid of water, and therefore it's not going to be interacting with it. And that's, again, because it's got that large carbon skeleton. Okay, and so this particular compound would not be miscible. So it would be immiscible with water. And that means that it basically doesn't mix. It's like oil and water, like I said. And then if something is miscible with water, it does mix. All right, so now that we're on this fatty acid, that brings me to something super fun, which is the application of solubility for soap. Okay, so soap, what you talking about soap for, right? Why is this relevant? Well, have you ever seen, let's see, oh, come on, bam, have you ever seen Fight Club? Well, if you have, you probably wouldn't tell me, because the first rule of Fight Club is that you don't talk about Fight Club, right? Well, if you haven't seen it, it's a great movie. You should definitely check it out. It's also a good book, but I'm not even going to front like I read the book. I just know that it's a good book from having friends that have read the book. So I probably will check it out eventually, though. So why is this relevant? Well, have you ever thought about why Fight Club symbol is a bar of soap? It's because they make soap in the movie. But what they do is they go to liposuction places and they steal fat, right? And so why do they steal fat? That's because they can get these fatty acids where they have boom, 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 boom. Really long chains, right? Those are fatty acids. And so you can get that from the fats that they obtain from that liposuction place. But then what you end up doing is converting this to basically a salt. So rather than having that carboxylic acid portion there, you form a carboxylate. Okay, and so basically it's an acid, right? You could just throw a base in there, like lye, it's just sodium hydroxide. And what that does is it removes this proton here, this acidic proton, and it forms an ionic compound. And what you have here is this polar head now, right? Polar head, and you have this non-polar tail. So this portion right here is that non-polar tail, non-polar tail, Okay, and so this is actually what soap is made of. It's made of, it's made from fats, and it makes, basically you have this carboxylate species here, and so I keep saying that word, carboxylate. So remember acid-base chemistry, when you add an H to the end of it sometimes. We don't need to review that, but this is a carboxylate, and the way this works is, since we have that polar head and that non-polar tail, we can abbreviate it as pretty much this, right? Let's just say this is our polar head, and this is our non-polar tail. Okay. Now, what happens is, in the presence of water, these, since they have that non-polar tail, the non-polar tail is hydrophobic, right? So it's scared of water and it runs away. And so what happens is you have all of these guys orient themselves as follows. Here, let me do this. I'm better at drawing circles in a circle if I do that first. Okay, so whoa, 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 whoa. Now you get the idea, right? So the outside, this region right here, is the polar portion, and this is interacting with water. Because remember, like dissolves like. Okay? And so it's almost like tricking water to sneak a non-polar substance in there, right? Because this inner portion is non-polar, and that means that you can hide grease and oil and other non-polar particles or substances in there. And so this is where you would have your grease and your nasty stuff, and so this would be kind of encapsulated inside of this thing called a micelle. Okay, so this whole cool little spherical thing is called a micelle. And that is pretty much how soap works in a nutshell. And there you have it. So since we're also on the topic of polar and non-polar heads and tails, you might also be familiar with how this concept comes into play for cell membranes, right? And so it's a little bit different in that the polar head is structurally different. However, we do have a non-polar tail, which is basically just carbon-hydrogen, a carbon chain or skeleton, right? And so for cell membranes, what we have is we've got a basically, here, let me just draw this for you. Wow, terrible. We got a nitrogen, and it's an ammonium group, so it has a charge, and therefore it has 4 bonds. And then we've got a phosphate group here as well. And this phosphate group is bound to some other stuff. And then sorry, I'm running out of space, but you get the idea. That's the very long non-polar chain. Okay, and so you get this phospholipid. Okay, and we have this negative charge and this positive charge. So this portion right here is the polar portion, or the polar head. Whoop. And this portion right here is going to be our non-polar head, or non-polar tail, sorry. Oh, stop it. Non-polar tails. Okay, and so this more or less works the same way as the micelle formed above, but we'll get something called a phospholipid bilayer. So lipid lipid bilayer, and you'll have pretty much the polar head coming down like this, and then you'll have another one where it comes up like this, and so you get boom, 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 down, 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 boom. Okay, and so this is your phospholipid bilayer, and so this portion up here is obviously going to be interacting with it's the ionic or polar head, and so that's what's interacting with the polar substances within our body, while the inner portion, the inside portion is going to be the non-polar, and that's that's going to have different things, like it could have proteins in there or cholesterol or things like that. And so very similar to the micelle and soap, but structurally a little bit different, but super important, right? Because cell membranes. And real quick, one last thing about some basically applications. So vitamins, right? I'm pretty sure you're probably familiar with like fat soluble and water soluble vitamins. So the ones you pee out and the ones that you can actually die or have adverse effects if you eat too much of them. So like vitamin E and A are fat soluble, and then like vitamin B's and C's are water soluble. So let's take a look at those structures and see how it kind of makes sense and according to the concepts we've learned, right? And so vitamin A looks like this. We've got boom, boom, cool structure, right, boom, 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 boom. Oh, come on now, buddy. All right, cool. 7 years later, I got my vitamin A down, and so what you can see is, hey, it does have a polar functionality, but it's also got a much larger portion that is non-polar, and so that's why vitamin A is fat soluble and not water soluble. Okay, because it is non-polar. It doesn't satisfy the solubility rules required to be soluble in water, in that one functional group that can hydrogen bond for every 5 carbons that are present. Okay, so there's definitely more than 5 carbons for that one functional group that can hydrogen bond. All right, so let's take a look at this one and let me know what you think. Is it going to be fat soluble or water soluble? Boom, 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 boom. Boom, 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 boom. Here we go. So, do you think it's fat soluble or water soluble? And if you guessed water soluble, you would be correct. And that is vitamin C. Whoa. JK. Vitamin C. And intuitively, you probably know this already, even if you didn't know vitamin C was a water soluble vitamin, because we often take vitamin C tablets that are like 8,000% of what our daily required value is, and that's just going to end up being peed out. So it's not harmful to consume too much, whereas I think if you consume too much vitamin A, don't quote me on this, I'm pretty sure it affects your eyes and you can potentially go blind. I might be making stuff up, but that's what I thought I heard as a wee lad. All right, so let's do a couple more. Let's see what you think they are. Boom. I like looking at these structures. They're really cool structures. They're elaborate, and structure and bonding in general is really fascinating to me when it comes to chemistry, because structure is really how we're dependent on the chemical structure of things in order for them to work within our body. And so if we can understand the chemical structures of things and how they like what enzymes they're interacting with, we can kind of make our own synthetic things and potentially help a variety of diseases, right? And so this is the idea behind synthetic organic chemistry. All right, so this guy right here, do you think it's polar, non-polar, and therefore soluble in water? I said therefore. Do you think it's polar and therefore soluble in water, or non-polar and fat soluble? So you got the carboxylic acid group, we got the nitrogen group, and we've only got 1, 2, 3, 4, 5, 6 carbons. So this is water soluble. And it's also vitamin B. Is the 3 go on the top or the bottom? I don't remember. This is niacin. Okay. And what about this next one? That's clearly got all kinds of non-polar bonds on there. This is vitamin K. Okay. So there you have it. That's pretty much vitamins in a nutshell. And again, I think the structures of these things are really cool, and understanding really how they work. Basically, on that note, let me add another one in here for you, a couple more that I find really interesting. So this one in particular. So are you guys familiar with adenosine? Adenosine? Yes, you are probably, if you've taken bio. Some sort of bio that talks about adenosine. I don't remember. It's probably cell bio. So maybe if you don't know it, that's why. It's maybe because you haven't had cell yet. But this looks a lot like adenosine, but it is not. And this is actually caffeine. I before E, except after C, or when sounding like "een" as in caffeine. So whatever. That's the structure of caffeine, and I mean, as far as I understand, that's pretty much why it works the way it works. It binds to adenosine receptors in our brain, and then basically prevents us from being tired. The more you consume, your body just going to make more adenosine receptors, and then therefore you need more caffeine to bind to those adenosine receptors, and then bada bing, bada boom, you're drinking 2 mocha chocolate yayas from Starbucks a day, and nothing is doing nothing for you. So I'm a caffeine fiend though, so I can't even talk like I'm not drinking it 3 times a day. Let's see another really cool one. Well, let's just talk about practice. Y'all want to talk about practice? All right. So answer the questions. Okay. All right. So there's going to be a bunch of the same of a bunch of different questions on the same structure. So we want to identify or ID the functional groups, and then we want to do classify any alcohol. Classify, I'll do ROH for alcohol. No, that's not, I don't want to abbreviate it. Alcohol, amide, or amine. And so remember, that's as primary, secondary, or tertiary. Which proton is most acidic? Most acidic proton. And let's see, we've got most basic site. Yeah, I told you there's about to be a lot. So what is the hybridization of the nitrogen atom? Hybridization of and then how many sp2cs are there? Okay, so what's the structure? So I'm fascinated again with chemical structures of drugs, actually, because I like to see the difference between, basically what they look like, and see their similarities, and kind of see what subtle differences are necessary to provide either the kind of the effects that they have, but also see kind of how that small effect really changes the, like, maybe like how addicting it is, or anything of that sort, anything of that nature. So sorry, this is weird. This is a very weird structure. So this very, very dark bond that I'm drawing right here, going to the nitrogen from this carbon over here, that's actually a ring that's sticking out at us. So this is more pretty much like a wedge sticking out at us, while everything else is, we're just going to act like that's in the plane of the board. And this is oxycodone. Okay, so this is the topic of the question, right? But so let me just do myself a favor here. I'm going to copy this, and I'm going to paste it right here, and I'm going to show you the difference between this as well as heroin. So heroin, for example, does not have this methyl group here and then this carbonyl group here. It doesn't have that there either, but it's still got that basic structure, that basic skeletal structure there, and it's got a carbonyl group here, and this is the same thing on that side, and it's got a double bond here instead. Okay, and let's take a look at morphine. So morphine is looking like this. Let's do that. Put it right there. All right, so we've got to delete that stuff. All right, so we're putting that OH back there, or that O there, put another OH there. We've got the double bond there, and this is morphine. All right, so look at the two structures here. These are extremely similar. The only difference here is that this is an acetyl group, and then the over here we've got these OHs here, the hydroxyls, and that's the only difference between morphine and heroin. This can actually be converted from morphine to heroin with something called acetic anhydride. Acetic anhydride, which is another functional group that you guys should be aware of. So this portion right here, where you have two carbonyls with this oxygen in the center, that's called an anhydride. Okay? Whoa. Simmer down, iPad. All right. That is called an anhydride. The reason why I'm bringing this up is because I legit just saw an article that was talking about basically finding drugs in Mexico and having a strong scent, like as you're driving by through these like desert areas and desolate areas, you can smell pretty much vinegar, a very pungent odor, and that's because this guy breaks down into acetic acid in the presence of water. So this is acetic acid, and this breaks down into acetic acid in the presence of water, and this particular acetic anhydride is purchased in like basically gallons from a U.S. manufacturing company, and then delivered to Mexico, which then they then use to convert morphine into heroin. And so just saw that article, so that's interesting. Why would you need to sell literal jugs of acetic anhydride, and then even then to Mexico? Like, I mean, that's a little sketch, right? The article I read, they were basically romping through an area that was desert and trees, and or like some area that was unseen and hidden, and then they smelled the vinegar, so they went off the beaten path and then found the stash. So really interesting stuff. Chemistry is in the news every day, you just don't even know it. All right, so back to this actual practice problem, stuff that's more relevant to the class. ID the functional groups. All right, so pause it and give it a try yourself, and then see if you get what I get. Okay, so I'm gonna go ahead and get started. We have this right here is an ether, and this obviously right here is an aromatic. This is an ether also. This is a cyclic ether because it's within a ring. This right here is a ketone. Right here, remember I said that it's called a hydroxyl, but I always put alcohol. So, and then this right here is an amine or amino group, right? And then we got obviously a bunch of hydrocarbons in there, but we don't really necessarily need to qualify those as functional groups. So let's do it in blue for the next one. Classify alcohol, amide, or amine as primary, secondary, or tertiary. So we do have an alcohol in here, and that is here. So this alcohol is bound to a carbon that's bound to 1, 2, 3 carbons. So the OH is equal to a tertiary alcohol, while the amine here, this amine is bound to 1, 2, 3 carbons as well. So the NR3 is equal to a tertiary amine. And we don't have an amide, so we are moving on. So let's try black. Most acidic proton. Where is the most acidic proton? So that's also the alcohol. Okay, so I'll put ROH here. And again, that's because remember the rules for determining the acidity of a proton. The first rule out of all the four, or the first effects out of all the four, was the elemental effect. So is that hydrogen bound to a heteroatom that's more electronegative? Yes, that's the only one that's bound to an oxygen or something not carbon, and so therefore that's the most acidic proton. Now, which is the more basic site? Now, just as a general trend, as we go from left to right within a row, the basicity of the atom decreases, and so that's why nitrogen would be more basic than the oxygen. Okay. Hybridization of that nitrogen, it does have a lone pair, and it is sp3. How many sp2 carbons are there? Well, there's 1, 2, 3, 4, 5, 6, 7. I don't think I missed any, so I'm going to go with 7. Okay, if I missed any, I'm sorry. Let me know. But that's pretty much it for that. So pretty good question. Lots of stuff to ask about it. So and I think you should know this. But also, if you're curious, Google drugs, and if those drugs that have the similar effect on the body probably have similar structures. Haha, so you want to talk about practice. Okay. So let's say we've got, this one's a little, this is actually in it's a difficult problem. Let's just go with that. Okay, so that's why I want to do it with you, because then you'll learn all kinds of stuff, because you're going to be able to do the hard problems. Okay, so we've got this guy right here. Remember, there's an alkene right here, and that pi bonds are not free to rotate. So although it is structurally similar to this guy, it is also very different. Okay, so these two structures, this is actually called a cis alkene, and this is called a transalkene, because this portion of the R groups on the alkene are on the same side, whereas on this one they're on opposite sides of the double bond. Okay, so this is maleic acid, and this is called fumaric acid. Okay, so the interesting thing about these is they have the same, more or less the same functional groups, but they are three-dimensionally different, right? So the three-dimensional orientation of this molecule is different, and so their melting point, their solubility, and their pKa's of each of the acidic protons is different. All of those. So there's 2 protons on there that are acidic in each of these molecules. So it has 2 pKa's. And for maleic acid, this is 130, this is 788, and that's in grams per liter in water. So per liter in water. And this is, the pK is 1.9 and 6.5. Okay, so nothing too crazy there, but let's take a look at the fumaric acid melting point, solubility, and pKa's. Those are 286. Now that's crazy, right? So this is degrees Celsius. So that's over 100 degrees difference. It's 150 degrees difference. That's crazy, right? 7 grams per liter is soluble in this particular compound. For this particular compound, and then 3.0 for the pKa, and then 4.5 for the pKa, the second pKa. Now, let's talk about why this is. So, for the melting point, what do we know about the melting point? Okay, so what do we know about melting point? We know that the more symmetrical a given compound, the higher the melting point. So this one's higher, and this one is in fact more symmetrical. More symmetry. And if you don't, this is also very symmetrical. This one right here, this maleic acid. However, this one is more symmetrical in that we have kind of hydrogens going along this way. If we were to cut it in that plane, we have hydrogens on one side and then the carboxylic acid on the other side. Whereas if we were kind of cutting through here, it's more or less the same thing on either side, right? We have a carbonyl group on this side coming down, and then an OH there, OH here, and a carbonyl going on the other side. So although they both look very similar, the fumaric acid is actually more symmetrical. And you can also see this in what we would assign the reason for our solubility. So solubility in water, remember, water is polar and like dissolves like. And so when we're thinking about that, well, which one's more polar? Even though they have the same functional groups, this one's actually, maleic acid is actually more polar. And you can see this in the direction of the dipole. So it would go more or less that direction and more or less that direction. So let's look at this one. We've got more or less that direction and more or less that direction. So they're actually opposing forces across that double bond here. And so this one, although they are both polar, probably some, right, because they have the carboxylic acid groups, those are definitely polar. And so, but the main component of it is actually going to cancel out these guys right here, whereas these ones are going to give us a net dipole in that direction. And so that's why this one is more soluble, because it's more polar. And that also kind of points to the idea that it is less symmetrical as well, because we do have symmetry is almost like mirror images, and this is opposing one another because they're opposite of one another, which would be like a mirror image. Okay, and so the pKa, see, this is an interesting one, super fun. I love looking at this stuff. Why are the pKa's different? Okay, so let's talk about pKa's real quick. Sorry, I wanted to get that out of the way. For the first pKa, we have pKa 1.9 versus pKa of 3. So let's just say we're ripping that proton off and that proton off. Okay, so we want to remember that if we were going to remove this proton what we would get is, let's take a look at the conjugate base, because that's what we always do when we are looking at the acidity of a proton. So Y is, Y is the conjugate base of maleic acid, more stable than fumaric acid. Think about it for a second. It's a pretty difficult one, but also super fun if you figure it out. It's very exciting, right? Well, let's take a look. We can rotate about this sigma bond. Let's rotate about this sigma bond, and what we end up getting is, so this is just a rotation, so everything else stays the same, except now this OH is here. Let's put that there, and the oxygen on the carboxylate is there, and the carbonyl is on the left. So what did we do? We put that straight up negative charge on the carboxylate directly near this delta positive proton, and so a positive and negative are coming closer together, and so there's going to be some interaction here and some stabilization of that negative charge beyond the stabilization that would be present from the resonance, because this guy has resonance too, right? And so that's irrelevant in that sense, but it does have the adjacent proton that can help stabilize the charge. If we rotate these bonds, what we get, let me fix that real quick. I don't like when my iPad tells me what to do. It's not my favorite. So what we're getting is that and that. So notice this negative charge is nowhere near that hydrogen, that delta positive, and so there's no stabilization in that sense. On that same note, take a look at the second pKa, 6.5 versus 4.5. We've got a higher pKa for the maleic acid now, rather than that significantly lower one. Or I guess it's one value, right? So it's 10 times more acidic on the first proton, but it's actually 100 times less acidic on the other proton, or on the second one, right? And so why would that be? Well, if we remove that second proton, so let's do minus H plus, and then we would get, we're already set up to explain it perfectly, and there you go. And then if you go here, we'll do a minus in H plus. We can leave it this one however we want. And those negative charges are nowhere near one another, whereas this one, remember, anytime you have molecules, there's always going to be bond rotation. However, when these ones rotate in this particular conformation, the negative charges are kind of bumping into one another, and remember, negative charges repel one another, and so this one's technically higher energy and therefore less stable, so the conjugate base is less stable, and therefore it is a weaker acid to begin with, and so that's why we get that difference in pKa. Okay, so great question, right? I love this one. It's very involved and incorporates a lot of different concepts, and it requires us to think very deeply about it. Love it. Hopefully everything went through clearly, and if you have questions, just let me know. But I will leave you with another fancy joke. So I got a question for you. What do you think the most annoying pepper is? The jalapeno, because he's a jalapeno business all the time. Dang. Back up. That's all, just mind your business. That's all, just mind your business. Fresh Prince again. What's up? Watch it. Love it. Bye.